Okay, so once again, welcome back to another lecture discussion video. So for today, we will be discussing all about equilibrium and elasticity. So for this topic, we have the subtopics that we will be discussing today, which are number one, the conditions of equilibrium. Number two will be all about the center of gravity. Also, we will be discussing all about the center of mass and how we would relate this to center of gravity. And then the last one would be all about the stress, strain, and elastic moduli. Okay, so now let's start with the conditions of equilibrium. So, first, before we proceed with the condition, let us first define what an equilibrium is. So, when we say equilibrium, it means na the object is at rest or stationary or it is not moving, or we can also say na the object is in equilibrium if also it is moving at a constant speed in a straight line, or in other terms, the forces are balanced. Okay, so again, what are the conditions for equilibrium? So we have two conditions for equilibrium. The first one we have right here, the forces acting on the object must be balanced. So according to Newton's first law, if you can still recall, Newton's first law states that the sum of all forces on the object is zero, or the sum of all forces or the net force acting on the object is balanced, meaning the resultant force is zero. So it also means if we are dealing with x, y, and z axis, so the sum of all forces along the x will be zero, the sum of all forces along the y will be zero, and also the sum of all forces along the z axis will be equal to zero. So that is the first condition. And also, the second condition is the turning effects of forces about a pivot must also be balanced. So it means na it must have no tendency to rotate. So this is based on the dynamics of rotational motion. So for the second condition, it means na the sum of the torque must be equal to zero, or it must be balanced. So the resultant torque must be equal to zero, or it must have, or this object must have no tendency to rotate. So those are the two conditions. So the first condition is based on Newton's first law. So the sum of all forces on the object must be equal to zero. And the second condition is the sum of all the torque of the object must be equal to zero, or this object must have no tendency to rotate. So again, those are the two conditions for equilibrium. Okay, so we have also here in figure 11.1 A, B, and C, we have this conditions or examples or situations in which the first condition or the second condition was satisfied. So in figure 11.1, we have here, to be in static equilibrium, a body at rest must satisfy these two conditions, meaning the first condition and the second condition for equilibrium. So it can have no tendency to accelerate as a whole or to start rotating. So in this, in letter A, the body is in static equilibrium. So the two conditions were satisfied. So as you can see right here, balance ang forces. So the net force we have we have the two times the amount of force downwards, and then we also have two forces upwards. So it will be cancelled out. So the net force is zero. So meaning the first condition was satisfied. Now for the second condition, the net torque about the axis is zero. So the body at rest has no tendency of rotating. It's because also of the forces nga balance or because of this equal nga forces, upwards and downwards. Now, for letter B, as you can see in the figure, the first condition is satisfied. So we have F amount of force going upwards and also F amount of force going downwards, which will be cancelled out. So the net force is 0. But for the second condition, so there is a net clockwise torque about the axis. So wala na satisfy si second condition, which is it must not rotate. So, or the net torque is equal to 0 because there is a net clockwise torque about the axis. And also for letter C, as you can see right here, we have F force upwards and also we have 2F force upwards. So, the first condition is not satisfied. So, ang iyang net force is not equal to 0 because they are on the same direction. So, if we will get the total or the net force, it will be equal to 3F. So, we sum up F plus 2F. So, we have 3F. But for the second condition, the net torque about the axis is equal to 0. So, the body at rest has no tendency to start rotating. So, the second condition is satisfied. So, again, these are the cases in which, when the conditions for equilibrium will be satisfied. Okay. So, now let's proceed to the center of gravity. But before we proceed to the center of gravity, I will be introducing you to the center of mass because they are related to each other. Okay, so when we say center of mass, let's have it as CM. So, center of mass is the point at which all the mass of an object is concentrated, or the point at which mass is equally distributed in all directions. So, as you can see here in the figure, these are the examples on how we would find the center of mass of this homogeneous object. So, we have here the clock. So, it is a circle. So, obviously, the center of mass is located right here. The second example is a TV. So, it is in a square. Let's say a square. So, the center of mass is right here, located right here. And for this tablet, or let's say we have an iPad, which is in a rectangular shape, so the center of mass is also located right here. But how about for cylindrical objects, or we have a cone? How can we find the center of mass of this object? So the center of mass for the cylinder is located on the axis of symmetry. So as you can see, the dots right here, this is the axis of symmetry of the cylinder, as well as for the cone, this is the axis of symmetry of the cone. So naa diri ang center of mass, or the center of masses of these objects. So the center of mass may or may not lie inside the object. So not necessarily na the center of mass is inside the object. So that is how you would determine the center of mass of different objects. Okay. So how about for the center of gravity? So for the center of gravity, it is the point where the whole weight of the body appears. So we have these two cases right here. As you can see, in case number 1, we have a soccer ball that is on the placement of your finger is at the center of the ball, whereas sa case number 2, it is not placed, or your finger is not placed on the center part of the ball. So what will happen on case 1? The center of gravity is right here. So let's say your CG. But because the force or the weight is going downwards, but the force that your finger exerts is upwards. So it will be canceled out. So what will happen to the ball? The ball will not fall down or dili siya mahulog. Whereas in case 2, as you can see, the center of gravity of the ball is right here. So the weight is going downwards, but your force, the force that you exert is going upwards. But in this case, it is not in line with the direction of the weight. So what will happen to the ball is it will fall down or mahulog siya. So again, center of gravity, or we can call it a CG, is the point where the whole weight of the object or of the body appears. So here, what is the difference between the center of mass and center of gravity? Now, in a uniform gravitational field, in which case here in Earth, uniform man nga to ang gravitational field, the center of mass is just equal to the center of gravity. Or we have Cm is just equal to Cg. So the only difference between Cm and Cg is that they appear on different points in a non-uniform gravitational field. So example of non-uniform gravitational field will be in the outer space or in another planet maybe. So let's say you put a tablet or an iPad here on Earth. Let's say we have an iPad right here. Okay, so the center of mass or the center of gravity of the iPad is right here. But in space or in another planet, we can have, or the center of mass or the center of gravity of your iPad will change or will appear at different points. So if sa Earth, diri ang atong center of mass or center of gravity, maybe on another planet or in outer space, the center of mass is right here or even right here. So dira na nato makita ang difference between center of mass and center of gravity if the object is in a non-uniform gravitational field, or in this case in space or in outer space or in other planets where we have different values of gravity or acceleration due to gravity. But here, since we are in uniform gravitational field, the center of mass is just equal to the center of gravity. Okay. So now, how to find the center of mass or center of gravity on an object? So let's say we have here for first figure, we have a bicycle. So how would we determine the center of mass or the center of gravity of the bicycle? So let's say you hang the bicycle on different sides. So let's say you put a string or whatever to measure or to indicate the center of mass or center of gravity. So let's say in this orientation, this is the center of mass or the center of gravity. And then you suspend again or you hang the bicycle in another part. So as you can see, we have another line right here. And again, we suspend the bicycle in another orientation. And then we have this another line right here. So as you can see, there is a common point. So this point right here is the center of gravity or the center of mass of the bicycle. So that is how we would find the center of mass or the center of gravity for an irregular shaped object. So we also have here in figure 11.4, which is a mug, coffee mug. So what is the center of gravity of this mug? So first step, suspend the mug from any point. So a vertical line extending down from the point. So you draw a straight line, passes through the center of gravity. And then for the second a step is to suspend the mug from a different point. So in this case, let's say you flip the mug on another side. So a vertical line extending down from this point intersects the first line. So this intersection right here is the center of gravity of the coffee mug. So wherever the intersection of the lines according to their orientation or according to their according to their orientation, so the center of gravity is located on the intersection of the lines. So that is how we would find the center of mass or the center of gravity. So now, we now know how to find the center of mass and the center of gravity. Now, how to calculate the center of mass or the center of gravity. Okay, so we have here an example in which we can find, or we will know how to calculate the center of mass or the center of gravity. So example, a uniform beam of 5 kilograms. So this is our beam, this brown line right here, holds up two masses as shown. So we have 22 kilogram mass and 15 kilograms the mass. So find the center of gravity of the system of objects from the left edge of the board. So from here. So we will find the center of gravity starting from the left edge of the board. So as you can see, the center of mass of this wood, or I mean this beam, since this is uniform, it is mentioned na uniform. So the center of mass is at the geometric center of the beam, which is, let's say, right here. So 3 meters, because the length of this beam is 6 meters. So again, the center of mass of this beam is located right here, which is at 3 meters. So okay, so again, we need to find the center of gravity of the system. So to find the center of gravity, the equation will be, we have x because again we are dealing with horizontal, c, g for center of gravity. The formula is, we have, as you can see, we have 3 masses. We have the mass of this first object, the mass of the beam, and also the mass of the second object. So we have m1 times gravity, so weight times distance. The formula is the sum of the weight times distance. So we have weight, m1 times g, times x1, x sub 1, plus we have mass, second mass times g times x sub 2, plus we have the third mass times gravity times x sub 3, divided by the weight of the 3 masses, which is m1 times g plus m2 times g plus m3 times g. Okay, so take note na, since we are in a uniform gravitational field, the acceleration due to gravity, or g, is uniform. So we can factor out g in both numerator and denominator. So all the gravity or the acceleration due to gravity will be cancelled out. Okay, so let's cancel out this one. So we are left with m1 times x1 plus m2 times x2 plus m3 times x3 divided by m1 plus m2 plus m3, which is the formula for the center of mass. Okay, so that's why, as I have mentioned earlier, na in a uniform gravitational field, the center of mass is equal to the center of gravity. Okay, so now we will be using this equation to solve for the center of mass or the center of gravity. Okay, so here we have M1 is 22 kilograms. 22 kilograms times x1. x1 is 1 meter. We have plus. M2 is, we have this 5 kilograms for the beam. So we have 5 kilograms times our x2 is, since we are getting the center of gravity from the left edge, so from here to here, so it's 3 meters. 3 meters plus M3 is 15 kilograms times our x3 is 4 meters. 4 meters. Okay, then divided by the sum of the three masses. We have 22 kilograms plus 5 kilograms plus 15 kilograms. Okay, so now if we will calculate that one, xcg or xcm, center of mass or center of gravity, if we will calculate that one, it is equal to 2.3 meters. So the center of mass or the center of gravity of the objects from the left, or starting from the left edge of the board or of the beam, is at 2.3 meters. So let's say at this point. So this is the location of our center of gravity or center of mass. Okay, so that is how we would calculate the center of mass or the center of gravity of an object or system of objects. Okay, so that is for the center of mass or center of gravity. Okay, so now we proceed with the different types of stress, strain, and also the elastic moduli. Okay, so before we proceed with the different types of stress, strain, and elastic moduli, we will define first what is stress, what is strain, and also what is an elastic modulus. Okay, so when we say stress, stress is the strength of the forces causing the deformation. So, mo ni siya ang definition ni stress. So, again, it is the strength of the forces that is causing the deformation of the object. So, it is force per unit area basis. So, that is stress. Now, how about for strain? Strain describes the resulting deformation. And then we have the elastic modulus is the proportionality constant between stress and strain. So to solve for the elastic modulus, we have elastic modulus is equal to stress divided by the strain. So this is according to Hooke's law. Okay, so the first type of stress and strain is about, or it is named as the tensile stress and strain. Okay. So, sa tensile stress and strain, you have here in the figure, this is the initial state of the object before we apply tension. So, when we say tensile is from the word tension. So, initial state of the object. Now, after the object is under tensile stress, as you can see, it expands. So, the force is perpendicular to the cross-sectional area. So, to solve for the tensile stress is equal to perpendicular force divided by the area. And for the tensile strain, it is the change in length, or we have final length minus the initial length. Final length is the length after the object undergoes tensile stress, and the initial length is before, or the initial state, or the initial length of the object. So again, tensile strain is equal to delta L, or the change in length, divided by the initial length. And then we have also Young's modulus, which is capital letter Y. So to solve for Young's modulus is also a type of elastic modulus. So it is a proportionality constant. So gimension here, we have elastic modulus is just equal to stress divided by strain. So si Young's modulus, it is the tensile stress divided by tensile strain. So if we will plug in their corresponding formulas right here, we have tensile stress is again force divided by area, and then strain is delta L over L sub O. So our Young's modulus, or Y, is equal to this one. Perpendicular force divided by area times, we have initial length divided by delta L, or the change in length. So these are the formulas for the tensile stress, tensile strain, as well as the Young's modulus. Okay, so we have here the units for tensile stress, strain, and also the modulus, or Young's modulus. So for tensile stress, we will be using Pascal. So we have 1 Pascal, or 1 PA. This is the shortcut for Pascal. 1 PA is equal to 1 Newton per meter squared, because again, our formula for tensile stress is force divided by area. So the unit of force is Newton, unit for area is square meters, or meter square. So again, 1 Pascal is equivalent to 1 Newton per square meters. And also for the tensile strain, there's no unit, or pure number only with no units. Now nga naman, it's because again, tensile strain is equal to delta L over L sub O. So L, the unit of the length, change in length, is in terms of meters, divided by L sub O is also in terms of meters, so it will be cancelled out. So there will be no unit for the tensile strain. So pure number only. And then for the Young's modulus, it is the same with the tensile stress, which is still Pascal. Okay. So now let's proceed with compressive stress. Okay. So kung ang first one is you apply tension to the object, this one is we compress the object. So we have compressive stress and strain. So for the compressive stress, actually the formula is just the same with the tensile stress and strain. Okay, so compressive stress is just equal to, again, perpendicular force divided by area. Compressive strain is equal to change in length divided by initial length. And also we still have Young's modulus, which is again stress divided by strain, which is still the same with the Young's modulus for the tensile stress and strain. Okay. So we have here an example for tensile stress and strain. A steel rod 2 meters long has a cross-sectional area of 0.30 square centimeters. So it is hung by one end from a support, and a 550 kilogram milling machine is hung from its other end. So the question here is, determine the stress on the rod and the resulting strain, and also the elongation. So when we say elongation, it is the change in the length of the object. Okay, so again, we need to find the stress, the strain, as well as the elongation. Okay, so we have right here, what are the given values? So we have our given values. We have the initial length, which is 2 meters. We also have the area, cross-sectional area, which is 0.30 square centimeters. Now, if we will convert this one into meters or square meters, it is equivalent to 3 times 10 to the power of -5 square meters. Because again, our unit for the length is in terms of meters. So we will convert the unit of area into also square meters. And then also, aside from that, we have this 550 kilogram. 550 kilogram is the perpendicular force. So we have 550 kilogram. But again, di ba, force is equal to, according to Newton's second law, force is equal to mass times acceleration due to gravity. So, okay, since again, it is perpendicular, so we will be using 9.8 meters per second squared. So, this is our perpendicular force. Okay. So, now, let's try to solve tensile stress. So, again, tensile stress is equal to perpendicular force divided by the cross-sectional area. So, we have 550 kilograms times 9.8 meters per second squared divided by the cross-sectional area, which is 3 times 10 to the power of -5 square meters. Okay, so now if we will calculate this one, our tensile stress will be equal to, we have 1.8 times 10 to the power of +8 Pascal. Okay, Pascal. So this is our tensile stress. Now, we are done with the stress. Now, the next one is to solve for the tensile strain. Okay. So, for the tensile strain, di ba, it is change in length divided by initial length. Or, since we don't have delta L, but we only have L sub O, or the initial length, we can also get, or we can also solve for strain by using the Young's modulus. So, by the way, the Young's modulus for a steel rod, wala na siya gihatag sa problem, but it is a constant value. So, Young's modulus for steel Y is equal to 20 times 10 to the power of 10 pascals. Okay. So, take note na si Young's modulus is stress divided by strain. Okay. So, diba, Young's modulus is equal to stress divided by strain. So, we have the value of stress. So, to solve for strain, using the Young's modulus and the stress, so strain is equal to the tensile stress divided by the Young's modulus Y. So, we have our tensile stress, which is 1.8 times 10 to the power of 8 pascals divided by our Young's modulus is equal to 20 times 10 to the power of 10 pascals. So as you can see, makancel out si pascals on both numerator and denominator. So 1.8 times 10 to the power of positive 8 divided by 20 times 10 to the power of 10 is equal to, we have 9 times 10 to the power of negative 4. So again, there will be no units, purely numbers lang. Okay. Now, the last one, we are done with the strain. Now, the last one is the elongation. So, for the elongation is delta L. So, delta L, or it is the elongation. So, to solve for delta L, since we have now the strain, tensile strain, and we have L sub O, so, to solve for delta L, or the elongation, delta L is equal to tensile strain times L sub O. Okay. So, we have right here, tensile strain is 9 times 10 to the power of negative 4 times our L sub O is 2 meters. Okay. So, 9 times 10 to the power of negative 4 times 2 is equal to 0.0018 meter. So, this is our, or this is the change in length after the stress, or after the, after the stress that was that we are putting in the steel rod. Okay, so again, the tensile stress is equal to force divided by area. Tensile strain is equal to delta L divided by initial length, but in this case, we don't have the delta L yet, so we use the formula for Young's modulus in terms of stress and strain. So, since given man si Young's modulus, but here in the problem is wala siya gihatag, but supposedly, naani siya sa table. The Young's modulus for different materials is also different depending on the material. So, again, the tensile strain in terms of Young's modulus and tensile stress, we have tensile stress divided by the Young's modulus, and for the elongation or delta L, we have tensile strain times the initial length, which is equal to 0.0018 meter. Okay, so that is for the tensile stress and strain. So far, we have discussed the tensile stress and strain as well as the compressive stress and strain. So, don't forget, the equations for tensile stress and strain and compressive stress and strain are just the same. Okay, but ang nakalahi lang sa tensile stress and strain and the compressive stress and strain is that the direction of your delta L. So, as you can see, in tensile stress, nadari located si delta L. But for compressive stress and strain, this is not the location of your delta L. So, again, it's different. But, again, the formulas or the equations for stress, strain, as well as the Young's modulus are just the same. Okay. So, how about for the bulk stress and strain? So, when we say bulk, it is all about the volume. So, when we say bulk stress, you can also have it as volume stress. Bulk strain is also known as volume strain. And also, we have the bulk modulus. So, kung sa tensile and sa compressive, we have Young's modulus or Y. For the bulk modulus, we have capital letter B. Okay. So, the formula for the bulk stress. Bulk stress is equal to the change in pressure. P is the pressure in the fluid. So, P is the same as you can see here, kani siya nga equation is the equation for tensile stress and compressive stress. So, but pag abot sa bulk stress or volume stress, the equation is now the change in pressure. So, if we are asked to solve for, if dili given si pressure, but given si force and area, so we can still solve for the bulk stress using this equation right here. So, how about for the bulk strain? Bulk strain is the change in volume divided by the initial volume. Now, kung sa tensile and compressive stress and strain, it is all about the length. Pag abot sa bulk stress and strain, we are dealing with pressure and volume. Okay. So, bulk strain is equal to, again, change in volume divided by the initial volume. And for the bulk modulus B, it is still equal to stress divided by strain. But in this case, we have bulk stress divided by bulk strain. So, it is equal to negative of delta P divided by the change in volume divided by initial volume. Now, nganong naman tay negative sign or minus sign? So, we include a minus sign in this equation because an increase in pressure always causes a decrease in volume. So, in other words, if delta P is positive, then delta V is negative. So, the bulk modulus itself, CB, will always be a positive quantity. So, again, we include this negative sign or minus sign in this equation because if the pressure increases, it will cause a decrease in volume. Okay, so again, this is for the bulk stress and strain. Okay. So also, the reciprocal of the bulk modulus is also known as compressibility. And it is denoted by small letter K. So when we say reciprocal, we have right here, K is reciprocal to the bulk modulus or 1 over B. So since B here is negative delta P divided by delta V over V sub O. So the reciprocal will be, again, when we say reciprocal, the numerator becomes the denominator and the denominator becomes the numerator. Okay, so now here, the denominator, which is this one, becomes the numerator, and our numerator sa bulk modulus becomes the denominator. So this is the formula for compressibility, or C, small letter K. Now, for the unit for bulk stress and strain, since we are dealing with pressure, the basic unit for pressure is in terms of atmosphere, or 1 atmosphere or 1 ATM. So, the shortcut for 1 atmosphere is ATM. So, 1 ATM is equivalent to 1.013 times 10 to the power of positive 5 pascals. Or, it is also equal to 14.7 pound per square inches. So, kung sa tensile and compressive stress and strain, we are using pascals, pag-abot sa bulk stress and strain is we will be using ATM. So, since again, the unit or the basic unit for pressure is in terms of atmosphere. Okay. So, let's have an example for bulk stress and strain. So, for bulk stress and strain, we have here a hydraulic press contains 0.25 cubic meters or it is equivalent to 250 liters of oil. So here, find the decrease in the volume of the oil when it is subjected to a pressure increase, delta P, which is equal to 1.6 times 10 to the power of positive 7 pascals, or about 160 atm. The bulk modulus of the oil, B, is equal to 5 times 10 to the power of 9 pascals, or about 5 times 10 to the power of positive 4 atm, or atmosphere. And its compressibility is K, which is equal to 20 times 10 to the power of negative 6 per atmosphere, or atm to the negative 1. Okay, so ang gipangita sa problem is the change in volume of the oil when it is subjected to a pressure increase. So as you can see right here, we have given, let's write all the given first. Given, we have delta P, which is equal to 1.6 times 10 to the power of positive 7 pascals, or it is about 160 atm. We also have the bulk modulus, which is 5 times 10 to the power of positive 9 pascals, or it is about 5 times 10 to the power of positive 4 atm. And then we have the compressibility K, small letter k, which is equal to 20 times 10 to the power of negative 6 atm to the negative 1, or we can also write it as 20 times 10 to the power of negative 6 per atmosphere. And also, by the way, the initial volume of the hydraulic press, which is 0.25 cubic meters. Okay, so now, how can we solve for the change in volume? Now, we have two ways to solve for the change in volume. Okay, so this is the first one. So the first one, to solve for delta V, is by using the formula from the bulk modulus. Okay, bulk modulus is, bulk modulus B is equal to negative delta P divided by delta V over VO, or we can also have it as, okay, so now to solve for, wait, I will erase this one. We are about to solve delta V. So to solve for delta V, let us multiply both sides with delta V over V sub O. So we have delta V over V sub O is equal to, times the bulk modulus is equal to negative delta P. So we have divide both sides with V, cancel out, so we have delta V divided by V sub O is equal to negative delta P divided by the bulk modulus, and then we have to multiply, last one is to multiply both sides with V sub O. Okay, I will continue this here. So, makancel out na siya. So, we have delta V is equal to negative V sub O times delta P divided by the bulk modulus B. Okay. So, we have right here, instead of using ATM, we will be using the Pascal nga values. Okay. So, we have negative of initial volume is 0.25 cubic meters times delta P is 1.6 times 10 to the power of positive 7 pascals divided by the bulk modulus, which is 5 times 10 to the power of positive 9 Pascal. Okay? So, makancel out si Pascal on both the numerator and denominator. Okay? So, delta V is equal to, so 0.25 times 1.6 times 10 to the power of positive 7, and then divided by 5 times 10 to the power of positive 9, it is equal to negative 8 times 10 to the power of negative 4 cubic meter. So this is the change in volume. So this is the decrease in the volume of the oil. Okay, so now how about the second step? So the second step will be using the compressibility K in solving for delta V. Okay, so let's try another method or another method to solve for delta V. So, di ba, compressibility K, diba, K is equal to 1 over B, which is now negative delta V over V sub O divided by delta P. So, this is now the equation for K. So, now, to get delta V, we need to multiply both sides with delta P. So what will happen is we have delta P times K is equal to negative delta V over V sub O. And then we have multiply both sides again with negative V sub O. So this will be cancelled out. So we have negative K V sub O times delta P is now equal to delta V. So this is now our another way or another equation to solve for delta V. But this time we will be using the not the Pascal but the ATM or the atmosphere na unit. Okay, so we have delta V is equal to negative K times initial volume times delta P. So substituting their corresponding values, we have negative of K is 20 times 10 to the power of negative 6 ATM times the initial volume is 0.25 cubic meter. And then we have delta P in terms of ATM is 160 ATM. Okay? Okay, per ATM or 1 over ATM then is si K. Sorry, I forgot. Okay, so what will happen is makancel si ATM and 1 over ATM. So again, for delta V, we are left with cubic meter. So negative of 20 times 10 to the power of negative 6 times 0.25 times 160 is also equal to negative 8 times 10 to the power of negative 4 cubic meter. Okay, so as you can see, we arrive on the same answer despite having different methods on how to solve for delta V. So again, as long as you know the different equations or formula for bulk stress and strain, So you can have different methods on how to solve for what is asked on the problem. Okay, so that is for bulk stress or volume stress and strain. And then we have the last one is what we call the shear stress and strain. So as you can see here in the figure, different again the formation for the shear stress and strain. So for the shear stress is equal to parallel na siya, parallel force divided by the cross-sectional area. Kung sa tensile and compressive, it is the perpendicular force. Pag-abot sa shear stress, it is the parallel force divided by the area. And for the shear strain, we have x over h. Now, x here is this one, the displacement, and h is the height of the object or initial state of the object. Okay, so again, shear stress is a parallel force divided by the area. Shear strain is the displacement divided by the dimension h of the object, and the shear modulus is, or capital letter S, is just equal to, again, stress divided by strain, but this time it is shear stress over shear strain. So we have right here S is equal to parallel force divided by area, and then divided by the strain is x over h, or we can also have it as this one. So parallel force divided by area times h over x, or the dimension divided by the displacement x. Okay, so I think that's it. So again, we have different stress and strain. We have the tensile stress and strain. We have the compressive stress and strain. We have the bulk or volume stress and strain. And also the shear stress and strain. Okay, so that's it. So thank you very much for listening to our lecture video, as well as watching our lecture video for today. So see you again on our next discussion. Thank you.